Welcome to Radio Frequency Integrated Circuits class, and in this, so we are in lecture number 4, unit 3, and we are doing passive impedance transformation. So far we discussed about L match, pi match, and T match, and today's class we will see another set of matches called as resonator matches, or we call them as tapped capacitor match. So there is another along with this tapped capacitor match, there is something called as tapped L matches also, right? So we'll see how this tapped L match work as an impedance matching network, and especially so this even this circuits, this tapped capacitor match or tapped inductance match, so this matching network also has the ability, as we have discussed in the case of pi match, because in the case of L match, the Q factor is automatically determined by the impedance transformation ratio. But in the case of pi and T match, we could actually segregate, or the extra degrees of freedom made you to make Q factor also as a like designer can actually work on Q factor, right? In a similar way, this tapped capacitor resonator or this tapped capacitor match also has the ability to set the values like center frequency, Q factor, and the impedance transformation ratio, right? And if you look at the places where we use this tapped capacitor resonator or this tapped capacitor match, they are mainly used in RF oscillators. You, probably in the unit 4 when we study about oscillators, we'll definitely discuss about this tapped capacitor resonator, which is used as used in oscillators. So let me just draw the circuit diagram of this tapped capacitor match. So we'll have a resistance where I need to transform to another value. Say we have a resistance. Let me consider the value of that resistance as some R2, right? So the tapped capacitor match is basically it uses two capacitors, one across this resistance and one more capacitance in this way, and let me name this as C2 and this as C1, and the reactive elements will be definitely again cancelled by an inductor which is placed in this form, and from this end we will be measuring our input impedance, or whatever the transformed impedance will be measured from this point. So we will call this as L, right? So this is how this tapped capacitor resonator looks like, right? So basically what we have is a capacitor tank, a tapped capacitor tank. So, and this, there are two capacitors, and the resistance to be transformed is actually connected from, or that resistance is tapped or taken from this point of the capacitor, right? So by looking at the network, probably you can see how this works, or how the transformation ratio need to be determined, or how to find what is the relation between this R in and R2, this R in by R2 or R2 by R in. So so far we discussed about the series to parallel conversion and parallel to series conversion. We proceed in the same way, in a similar way. First we do we have these two elements, right? R2, are you with me? Are you following? Can I get a response in chat box? Are you guys with me? 31 participants. All right, yeah. So R2 C2. So the first step is actually to transform or convert this R2 and C2. So converting this R2 and C2. So this parallel will be converted into series. That is first step. So let me write down that here. The step one is actually to uh, convert the parallel section R2 C2 to series form. So when I convert this parallel R2 C2 into series R2 C2, I'm just naming it as R2S and C2S. So both R2 and C2, now it is in series form. Now to get the value of R2S and C2S, we already know how the series to parallel transformation works, and we can actually use the Q factor formula, and we can write the resistance value as well as the capacitance value. Thank you for the response. This is first step. Now, if I do this transformation, the equivalent circuit will be something like this. We'll have inductance, then a capacitance here whose value is C1, then another capacitor here whose value is C2S, and a resistance here whose value will be R2S. This is L, right? So this will be the resultant equivalent circuit after step 1. Right. Now the next step is, so soon after doing this, what we will do is, so the C1s and C2s will definitely, the equivalent will be, so two capacitors in series, the equivalent will be 1 by C1 plus 1 by C2s, right? So we will get the equivalent of that. And that can be transformed in now if you look at this section, now if I look at this section, this branch, I have an equivalent capacitance. So C1 and C2s are in series, so I'll have an equivalent, that equivalent and a resistance, so that again form a series RC section. So my step 2 will be to convert so let me write this as the equivalent as C equivalent. So or I'll write this as convert C1 this C2s R2s. This is a series, right? So convert this series section to a parallel section. So when we the parallel section will be again having a resistance. I'll call it as the final resistance or something. Let me mark it as 1 second. Yeah, now this is R2S, right? So that I'll be taken as R2P along with a capacitor. So equivalent capacitance R2P CT or something, right? We will name it accordingly, and so that equivalent circuit will be in this form. You'll be having a capacitor and you'll be having a resistance. Resistance is R2P, this is CT and this is L, and from here what we see is this R in. All right. Now, so how this works, how this matching network works at the resonant frequency, the impedance offered by RLC is only of R2P, and through that we will get a relation between this Rin and R2P, right? So basically what we want is a relation between Rin and R2, because R2P is same as Rin, because you can see that R2P is connected and the resistance seen from here is R2P only. So the relation what I want is the relation between Rin and R2. So that will give you the impedance transformation ratio. I hope you understand what is the procedure I'm going to follow now. So I'll first do this parallel to series conversion, then find the equivalent capacitance, then I'll do series to parallel conversion, and then thereby obtain a relation between Rin and R2, right? All right, so let me do that one by one. So since there are multiple transformations, you may be there will be a lot of formulas, so there will be a lot of equations what we'll be writing, but that should be okay if once you are comfortable with series to parallel and parallel to series transformation, these equations will be easy for you guys, right? So before I start, let me write. Uh, so before I start, let me write the Q factor. Okay. So I'll do step by step. First, let me write the Q of the network. So Q of the network is what I have. The network is R in L, C1, C2, and R2. So from this, I can definitely write the Q of the network as Q can be written as uh, R in divided by omega naught into L. This is one way to write, right? Or from this I can actually get the expression for L. So L can be determined. So if I know the Q factor and if I know the center frequency and if I know Rin, I can get L. So what is L? L is equal to Rin divided by omega naught into Q. So this is straightforward. So whenever a specification is given with a center frequency, bandwidth and impedance transformation ratio, you can directly find the Q factor, and then with Q factor and with the impedance transformation ratio means that definitely will have the value of Rin, and with omega naught you can find L. So that will be the first step. So the element L is not undergoing any kind of transformation. So L can be directly obtained from the Q factor of the entire network. All right. So that is step one. now, now let us go to the innermost RC, parallel RC section, and from there we will start. Okay. So I have a R2 C2 parallel section, right? There is an R2 C2 parallel section. So that will actually give you a Q factor. So what is a Q factor of this section Q2? Can I get a response in chat box just to make sure that you guys are there? So what will be the Q factor of R2 C2 parallel section? Yeah, it is omega RC. Very good. So it is equal to omega naught into C2 into R2. Right, I am calling it as Q2 because the overall Q we have for the entire network, and now this Q2 is only for this RC network, right? The Q factor of the RC network, the parallel RC is what? Yeah, I'm seeing the response from you guys. Yes, thank you. So omega naught into C2 into R2 is the Q of that particular network. Now, as I mentioned before, so I'm just rewriting it as so a two-step transformation I have done in order to convert this tapped capacitor match into a final parallel RLC. Now, for the derivation, I'm actually using different steps here. So R2 C2 Q factor we have written here. Now, let me go to next step. Let me call it as step 3, and there I'm actually doing this transformation. So I'm transforming this parallel R2C2 into a series section. I'm transforming this to a series section, and while doing the transformation, so this is basically what I have here is a capacitor C2 and a resistance R2, right? So this is now transformed into a capacitor C2 and a resistance R2, but I'm naming it as C2S and R2S, right? Now let me write the relation between this. So I can write that R2S is equal to the resistance value R2 divided by Q2 square plus 1, and similarly I can write C2S is equal to C2 into, so if you remember, we were always writing in terms of parallel resistance. Now it is series. So R2 is the parallel component and R2S is the series component. So C2S can be written as C2 into Q square plus 1 divided by, sorry, Q2 square plus 1 divided by Q2 square. This is C2S, right? So here already we defined what is Q2. Q2 is actually the Q factor of the parallel R2C2 section. All right. Now, I hope this is clear. If you have doubts, you can put in the chat box. Now, let me move to the next step. I'll call this as step 4. and this step is basically to find the equivalent capacitance. Now let me look at the network here. I'm just ignoring the inductance. So I have C1, then I have this C2s, then I have this R2s, right? This is what we have now. Now let me find the equivalent capacitance. So what is the equivalent capacitance? So the equivalent capacitance here is, I can, so since two capacitors are in series, I'll write the C equivalent is equal to 1 by C1 plus 1 by C2s, right? But what is C2s? C2s we have written here as C2 into 1 plus Q square divided by Q square, or I can write this as C2 into 1 plus 1 by Q2 square, right? Either way, both are right. Now I'll substitute that here. This can be written as 1 by C1 plus 1 by C2 into 1 by C2 into 1 plus 1 by Q2 square. Are you guys with me? The equivalent capacitance is this. Or this can be further written as C equivalent is equal to, can one of you solve and tell me what will be the equivalent capacitance? Sai Sumant, are you there? Sai Sumant? Sai Sumant is not there. Prakash Bhatt?
Yes, sir.
Yeah, Prakash, can you tell me
We'll
what
get
is the equivalent?
C1 C2 into 1 plus 1 by Q square whole divided by
Hmm.
uh, the C1 plus C2 into 1 plus. Yeah, I didn't simplify it. I'll do it in a minute.
All right, yeah, do it. No issues. Yeah, I think Nikhil has written the answer C1 C2 into 1 plus Q2 square divided by, is this correct? C1 Q2 square plus C2 into 1 plus Q2 square. Yeah, all
Yes,
Q are
sir.
Q2, right? Yes. I hope so. Sai Sumant is not there, right? Okay. So this is C equivalent. C equivalent is C1 C2 into 1 plus Q2 square divided by C1 Q2 square plus C2 into 1 plus Q2 square. Or this can be, sorry, so this can be further written as, how will we write this? Yeah, so 1 plus Q2 square I can actually take common. So in that case, I can write, sorry, you can write this as C1 C2 by C1 plus C2 into 1 plus Q2 square. So what I'm doing here is, I'm assuming, I'm just giving an assumption here. If Q2 square is larger than 1, this 1 I'm just neglecting, and I'm writing this as uh, this divided by Q2 square. Right, both are same, just if this Q2 square is larger than 1. Yeah, in numerator also we can do, then we will write it as 1, right? Yeah, we can do that. So equivalent CQ is very close to C1 C2 by C1 plus C2. This is valid when you have a larger Q, right? So just to make it simplify in the denominator, I wrote in this form. Now 1 plus Q2 square by Q2 square also will be very close, because if Q2 square is large, then this will not matter at all. Yes. All right. So yeah, so this is the equivalent capacitance. Now, so how can I write the Q factor of this series network? So what is the Q factor of this branch? Q factor of C1, C2S, R2S branch. So I can write the Q factor of this branch as it is either 1 by omega naught into R2S into C equivalent. Now C1 and C2 C2S in combination is giving you C equivalent. So I can write the Q factor as 1 by omega naught into R2S into C equivalent. Now this can be further simplified. If you look at this, uh, what is R2S here? Okay, let me go to the next page. Yeah, so this is the Q factor of the series, Q factor of the branch, what I have written now. And I can further written this, write this Q as 1 by omega naught into, what is R2S? R2S is basically, I think we have written that here. All right, yeah, correct. So let me write this R2S into, one second, omega naught into R2S into C equivalent. Now what is R2S in terms of the original resistance R2? So R2S is R2 by Q2 square plus 1. So I'm just replacing that omega naught into R2 by Q2 square plus 1 into C equivalent. Now what is R2? R2 can be further written as yeah, from this R2 is Q2 by omega naught into C2. So I'll bring in that also. R2 is what is R2? Q2 by omega naught into C2. So Q2 by omega naught into C2 into Q2 square plus 1 into C equivalent, right? So I have written the Q factor of the branch C1, C2S, R2S as Q equals 1 by omega naught into R2S into C equivalent. That is equal to 1 by omega naught into Q2 by omega naught C2 into C equivalent by 1 plus Q2 square. Right. So omega naught will get cancelled from this. So I can further write this as so if I put for C equivalent the above value, I think I can you substitute and let me know what will be this, the Q factor, by bringing the C equivalent term also. So let me write this as omega naught is not there, C2 into Q2 square plus 1 divided by Q2 into, let me bring in the C equivalent term here, which is C1 C2 divided by C1 plus C2 then 1 plus Q2 square into Q2 square, right? Or this can be written as is there a doubt? R2S. No, I'm just asking Nikhil, Sarvesh, and Sai Shekhar. You're writing R2S. Did I make some mistake here or?
No, sir. Like when you previously asked, we all just wrote the
Oh, okay.
expression
Sorry,
down.
sorry. Okay, no issues. Yeah. So now if I simplify this, I can write this as C1 C1 Q2 square plus C2 into check whether this is correct. 1 plus I think this is C1 and this is C2
Yes,
Q2
sir.
C1. Yeah, all right. So this is the Q, right? Now again, if I am considering Q2 square larger than 1, I can simplify this Q and write this Q as Q2, right? Because Q2 square Q2 into C1 plus C2 divided by C1. I think we can write in this form. So C1 plus C2 divided by C1, which is Q. All right. Now, so what we have now is, so what we are in the second step. Sorry, we are in the fourth step where we converted the parallel into series and we wrote the equivalent capacitance, and with that we defined the Q factor of that section. Now, the final step is now we have a series RC. Now, this series RC has to be converted into parallel RC. So let me go for step 5, where series RC. So the R here is R2S. R2S C equivalent is converted into parallel RC. So let me call this as R2P and C as the final T. So into R2C, this is actually the parallel section, right? I think I use the same notations in the first diagram also. Yeah, L, C, T and R2P. Yes. Okay. So going back to that, so series to parallel. Now what I have here is inductance L, a capacitance here, I call it as CT, and the resistance here, which is, I'm calling it as R2P, but R2P is same as R in here because the resistance seen across this is same as R2P at resonance, right? Yeah. So now if I write the Q factor of the series to parallel, I can state the Q factor as omega naught into Rin into CT, or I can write this as Rin divided by omega naught. This we have already taken. We have written as the first step, right? Now, what is this Rin? Rin is same as R2P, and that means that is same as R2S into 1 plus Q2 square, isn't it? Let me check. Yeah. Okay, now yeah, this is the Q what we wrote the previous Q. This Q square, right? Yes. So Rn is the same as R2Q, which is R2S into 1 plus Q square, where we define the Q of the series RC section just before, right? I hope this is clear, and this can be written as, now I can write this R2S in terms of R2 as R2 divided by 1 plus Q2 square into 1 plus Q square. So is this clear what I am writing now? Is this clear? All right, so Rn is, I am writing Rn now in terms of R2. So Rn is
Yes, sir.
equal to R2 into 1 plus Q square divided by 1 plus Q2 square. So I just defined Q2 and Q in two different points, right? So I defined Q2 for the initial parallel RC section, and then for the series RC section, I'm using the Q factor as Q itself. Now, okay, so now I am from this equation, from the equation of Rin and this R2, I am writing an expression for Q2. So how can I write an expression for Q2? So Q2 can be written as, when I bring Q2 here, Q2 can be written as under root of R2 divided by Rin, right? R2 divided by Rin into 1 plus Q square minus 1, right? This is the expression for Q2. All right. Now, so this is Rin. Rin we have written. Now what is CT? CT can be written as the equivalent capacitance C equivalent divided by 1 plus 1 by Q square. I hope this is also clear. All right. So since we have written all these things, now we can directly write the transformation ratio, or what is the relation between this Rin and RL, right? So how will I do that? Now I know that Rin divided by RL, sorry, Rin divided by R2, which is equal to 1 plus Q square divided by 1 plus Q2 square. Okay, let me take this to the next page. I hope this is clear. The final step what I have done here is series R2S C equivalent is converted into a parallel section, and after that I have defined the Q factor and the new values. Rin I define in terms of R2P, in terms of R2S, CT also I define. Now bringing the final thing here is the relation between Rin and R2, which is 1 plus Q square divided by 1 plus Q2 square. Now can you tell me what is if you consider, so if I consider Q square as much greater than 1, sorry, Q square much greater than 1 and Q2 square also much greater than 1, can I get the value of Rin by R2? So what is Rin by R2 in that case? So I have the value of so Rin by R2 can be directly obtained from here. So I can write this as Q square by Q2 square. So I think that can be directly written in terms of the capacitor value. So what is Q square by Q2 square here, which is C1 plus C2 divided by C1 the whole square, right? So this can be written as which can be written as C1 plus C2 divided by C1 the whole square, or this Rin by R2 is same as 1 plus C2 by C1 the whole square, right? So this is true when your Q square and Q2 square both are larger than 1. All right, I have used the same notation Q for overall Q and in step 4 too. Okay, what is my step 4? Okay, step 4 I have used this series RC section Q. Now step 5.
Sir, both step 4 and step 5 have the same notation Q. So can we use a different notation for step 5?
One second, let me just check.
Yes, sir.
So this is your final this is the series to parallel conversion, right? So but no, this is series to parallel conversion, right? So I have where it is. No, here I define the Q factor as Q. Now when I transform this series to parallel R, I have written in terms of Q. It has to be written in terms of Q only, no?
Oh, okay, sir.
Correct, no? Come again, series and parallel.
Sir, isn't that
No,
series
see,
and parallel have the same Q
yeah,
as
I got it.
design?
Maybe the difference is here. See, you can see that this is a small LRC section coming here, right? So for this, I have used actually a different Q. And but whenever it has come to this larger network, after the first transformation, what I have is actually a single network, including this L, right? So for that, I have used the same Q. Maybe there you got confused. So since this is a smaller section here, because this is not the this RC and this R2 C2 I was treating actually separately. That is why I put it as Q2. Once it is transformed, and for this network I'm actually writing it as Q. So that Q can be in terms of capacitance here, the equivalent capacitance, or it can be in terms of the inductance here. All right, I hope that is clear. Okay. All right, so if you have questions you can ask, otherwise we'll just take up the same example of yesterday. So I think I have given a question here. The same question we'll continue to get the values for this. All right, yeah. Okay, so design so design a tapped C match for the following specification. Given that F0 is 1 giga, R1 is 50, R2 is 5, and bandwidth is 25 megahertz. Right. Rakshak, come again.
Sir, I didn't understand how C match is better than pi match, because even in that I could adjust for all these parameters.
No, I did not say that this is better. If you remember, this also has the ability to set F0 Q and transformation ratio as same as pi match. I was telling it is different from L match. Probably I don't know whether when I used L match and pi match I used it alternately. I don't know. Compared to L match, pi match is having one more degree of freedom, right? The same thing is there for this tapped capacitor match also. All right, yes. So can you guys try this? So get me the values for the resistors, capacitors, and other things. What I will do is, when you are calculating that, I'll just set up the cadence and we'll just try the simulation and see the resistance values. Sorry, yeah, the impedance transformation ratio. We will verify. Okay, so how will you proceed and how will you, which all equations will you use? Let me just probably one equation what you will use is this, the inductance value, which can be directly obtained initially itself. Then yeah, so with that I think you will go ahead and find this value, which is, yeah, let me just listen to you guys. And okay, L is coming around 19.89 pico. That is right. Yes. Oh, can you check again? Is it 19.9 or yeah, 0.199 Henry, right? So it should be 199 pico, right? Yeah, L is that. Go ahead and find the rest of the things. Yeah, Purushottam, it is 199 pico. Now, what about other values? So I should get the value of C1, C2, yeah, C1 and C2. So any answer for capacitance C2 and C1? Rin is 5. No, R2 is 5. Right, Rin is 50, right?
So, but here R2 becomes our Rn, no, sir. Sir, was the question changed again?
No, no, this is a question.
So then R1 should be our R2.
Yeah, right. Yeah, right. Yes. Yeah, right. So I should yeah, R1 is actually a load resistance. So let me mark it as RL. So you can use the notation comfortably. Just to understand, I'll use here this as RL and this as Rin. Yeah, so with that you will get a different L. Okay. Can you check again, because I'm getting this as the answer. So Rin is
So is the in the question, are we supposed to perform downward conversion or upward conversion?
yeah, RL is 50, right?
Yes, sir. So this is upward
Oh,
conversion.
sorry. I think sorry. I confused you guys. Just a minute. So we need to what we did last class for L match this question. R1 was converted into R2, right? R1 was 50 and we have done down conversion.
Yes, sir.
Right. Isn't it? We converted R1 into R2, right?
Yes, sir.
Okay, the same thing. It is same thing only then. Yeah, that only I have written here, no? Am I confusing? I am not understanding.
Sir, according to this one, Rin is lesser than RL, and we're converting RL to RL. That's what he has written here.
No, I am not getting. No, whether I made a mistake, because the transformation should be from R1 to R2 or from RL to Rin only.
Yes, so this is down conversion only.
Yeah, it is down conversion. Yes. Is this clear or?
Yes.
With that, Mayuka, you are also getting 19.89 pico.
Yes, sir.
Oh, I think people are getting different answers. 0.01989 nano. Okay, let me write that here. L can be obtained from our first equation. Where is it first equation? L is R in by omega naught into Q. Right. What is R in? Which is 5 divided by omega naught into Q is 2 pi into 1 giga into, what is Q here?
So we
40.
can take 40, right?
Yeah, it is 40, yes. So what is the answer for this?
It's 19.89 picohenry.
All right, okay. Okay, now if you are taking Rn as 50, then it will be 0.199 nanohenry, right?
Yes, sir.
Sir, if we switch RL and RN, wouldn't it become up conversion?
Huh? Come again?
If we took RN as 50 and we switch them both, wouldn't it become up conversion?
I'm not getting.
Like you said, if you take 50, we get that value.
Yeah. No,
If
I'm
we
just.
switch them, it will become up conversion.
Yeah. It will become up conversion definitely. I'm just trying to understand. Like, did I make any mistake here by? Mm, okay, just a minute. Okay, can you just tell me the value for the up conversion? So considering this as R in and this as RL. Let me just check the final answers what I have.
So for the up conversion, we'll get 0.198 nanohenries.
0.198. Yes. Okay. So if this is 50, then your answer is 0.198 nanohenry, right?
Yes, sir.
Okay. So this conversion can be up or either down. So let me sorry. Can you get me the values for C1 and C2 for this? For this up conversion, yes. Get the values of C1 and C2. Q2 is 126. Okay, I do not have the value of Q2 with me. Yes, it should be definitely a higher value. 40 square plus 1 into, yeah. So just let me know the final value of C1 and C2. I don't think we can. I can show the simulation today. It's time up. Okay, so you can find out the values and just message even in the WhatsApp group. Yes, answers are very close to that. Capacitor C2, C2 is 0.401 nano. Yes, correct. Which is same as 401 picofarad. And what is C1? Any answer for C1? 0.185 nano. Yes, it is 185 picofarad. Very good. So I think you would have used all these formulas here to arrive at the final. So L you would have used, then yeah, you would have used this Q2 formula. then yeah. All right, so C1, the answers are right. C1 is 185 pico and C2 is 401 picofarad. All right, so now one more, the last match what we have to do is same like a tapped C match, we have something called as tapped inductor match, where now what we have used for the capacitors, so we'll just interchange capacitors and inductors. So that will be the last match. So we'll see, look at that match in the next class, and we'll also see the simulation, and after that we'll go for the second half of unit 3. So thank you so much for joining. If you have doubts, please put in the doubts forum. I can clarify that, or you can check here. You can ask with me here itself. Thank you so much for joining.